Imagine you are the manager of the grandest hotel in the world. It stretches endlessly in both directions, corridor after corridor of polished marble floors and brass room numbers, its hallways lit by chandeliers that fade into a golden haze in the distance. Every room is numbered. Room 1, Room 2, Room 3, and so on without end. This is the Hilbert Hotel, named for the mathematician David Hilbert, who first described it in a lecture in 1924. It has infinitely many rooms, and on this particular evening, every single one of them is occupied. The sign above the front desk reads "No vacancy." Then the door swings open and a traveler walks in. They are tired, they have been on the road for hours, and they need a room. Any ordinary hotel would apologize and send them away. But you are the manager of the Hilbert Hotel, and you simply smile. Of course, you say, "We have room." Here is what you do. You pick up the house telephone and make an announcement to every guest in the hotel. "Ladies and gentlemen," you say, "please pack your things and move to the room with the number 1 higher than your current room." The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. Room 3 moves to room 4. This instruction travels down the corridor forever, each guest nudging one step further along, a ripple passing through an infinite sea of rooms. When the movement settles, room 1 is empty. The traveler checks in. The hotel, still full with infinitely many guests, has made room for one more. This is not sleight of hand. This is how infinity actually works. When you moved everyone up by 1, the total number of guests did not decrease. There are still infinitely many people in the hotel. Infinity plus 1 is still infinity. The set of all natural numbers and the set of all natural numbers starting from 2 are exactly the same size, because you can match them up perfectly, 1 to 1, without gaps. Every number has a partner one step ahead of it forever. Now suppose something more dramatic happens. A bus pulls up outside, not a bus with 20 passengers or 100 or 1,000, a bus with infinitely many passengers, each one assigned a seat number. Seat 1, Seat 2, Seat 3, going on forever. The hotel is still full. Can you fit them all? You can, and the method is just as clean. You announce that every current guest should move to the room whose number is double their own. The guest in room 1 goes to room 2. Room 2 goes to room 4. Room 3 goes to room 6. Every current guest ends up in an even-numbered room. All the odd-numbered rooms are now vacant. Room 1, Room 3, Room 5, Room 7, an infinite supply of open doors. Passenger 1 from the bus takes room 1. Passenger 2 takes room 3. Passenger 3 takes room 5. The pattern holds forever. Every passenger has a room. Nobody is left outside. What this demonstrates is one of the most counterintuitive facts in all of mathematics. The set of even numbers is the same size as the set of all natural numbers. This feels wrong. Surely there are fewer even numbers, since they are only every other number. But size in mathematics means something precise. Two sets are the same size if you can build a perfect one-to-one correspondence between them, matching every element of one set to exactly one element of the other, with nothing left over. Multiply any natural number by 2 and you get an even number. Divide any even number by 2 and you get a natural number. The pairing is perfect, and it works forever. The two sets are, in the mathematical sense, equal in size. Now the lobby doors open again, and this time what arrives is not a single bus. It is an infinite convoy. Bus 1 pulls in, carrying infinitely many passengers. Then bus 2 behind it, also carrying infinitely many. Bus 3, bus 4, bus 5, an endless line of vehicles, each one full. Infinitely many buses, each carrying an infinite number of people. Can the Hilbert Hotel still absorb them all? It can. The argument requires a slightly more clever arrangement. Imagine laying out all the passengers on a grid. Bus 1 fills the first row. Bus 2 fills the second row. Bus 3, the third, and so on, the grid extending infinitely in both directions. Every passenger in every bus occupies exactly one cell of this infinite table. The challenge is to assign each cell a room number, visiting every cell exactly once, missing no one. If you try to go row by row, reading bus 1 completely before starting bus 2, you will never finish bus 1. There are infinitely many passengers in it. You will never reach bus 2 at all. The solution is to move diagonally. Start at the top left corner. Bus 1, passenger 1 gets room 1. Then step down to bus 2, passenger 1 who gets room 2. Then step diagonally up to bus 1, passenger 2 who gets room 3. Then down to bus 3, passenger 1 for room 4. Then bus 2, passenger 2 for room 5. Then bus 1, passenger 3 for room 6. The path zigzags through the grid, sweeping back and forth across the diagonals, and in doing so it touches every single cell exactly once. Every passenger receives a room number. The infinite convoy is fully accommodated. This zigzag path is the heart of a concept called countable infinity. A set is countably infinite if its elements can be arranged in a list that goes on forever but visits every element eventually. The natural numbers are countably infinite. The integers are countably infinite. The rational numbers, all the fractions, are countably infinite, provable by the same diagonal argument. These sets all share the same infinite size, a size mathematicians call Aleph null. And yet not all infinities are equal. Suppose a final bus arrives. This one carries a passenger for every real number between 0 and 1. Not just the fractions, but every decimal that can ever be written, including the ones that go on forever without repeating, like the square root of 2 minus 1 or pi minus 3. No matter how cleverly you try to list these passengers, no matter how intricate your zigzag, you will always miss someone. For every list you write, there is a number hiding in its gaps, provable by a method called Cantor's diagonal argument. You construct a new number by changing the first digit of the first passenger's number, the second digit of the second passenger's number, and so on, ensuring the new number differs from every entry on your list. The list can never be complete. This infinity, the infinity of the real numbers, is strictly larger than the infinity of the natural numbers. The Hilbert Hotel cannot fit this bus. The manager, for the first time, must turn someone away. And that is perhaps the deepest lesson the hotel has to teach. Infinity is not one thing. It is not a number at the far end of the number line. It is a landscape with its own internal geography, full of different sizes, different structures, different surprises. The Hilbert Hotel exists at the frontier of that landscape, a thought experiment that stretches intuition until it snaps, and then shows you quietly that the mathematics was right all along. The sign above the front desk still reads no vacancy. It always does. There is always room.